Hi, welcome to BC Video 12.3 Part 1, Introduction to Velocity and Acceleration Vectors. Okay, so we have our original vector valued function. This is now going to be referred to as our position function, and I'm actually going to compare that to last year. So if you remember last year, we had what was called rectilinear motion, which was motion along a horizontal or vertical line. So remember the dropping and the tossing of the object and from the top of the building. And this is just, particle traveling along, traveling along a horizontal line in the vertical motion. So we had a position function, which last year we called S of t. The velocity function, of course, you remember, was the derivative of the position function. We refer to it as v of t. Remember, speed was the absolute value of the velocity function, and the acceleration function, of course, was the derivative of the velocity function, making it the second derivative of the position function. And again, don't forget that the speed was the absolute value of the velocity. Well, what's going to happen in BC is we're going to be not looking at only the motion along a line, but the motion along a curve. It's called curvilinear motion along a curve. So instead of our position function being, S of t equals, and then you have a function of t, or s is a function of t, you're going to have a position vector, r of t equals x of ti plus y of tj, which you can write in component form if you'd like. The velocity vector, just like over here, the velocity is the derivative of the position function. Here, the velocity vector will be the derivative of the position vector. So, and now remember, to take the derivative of a vector, you take the derivative of the x component. You'll still stick that vector I, that unit vector I on it, and then the derivative of the y component and stick the j on it. The acceleration vector, very predictably, is the derivative of the velocity vector, making it the second derivative of the position vector. So if your velocity vector is x prime of ti plus y prime of tj, the acceleration vector would be the second derivative of x of ti plus the second derivative. Now, for speed, and this is mentioned very briefly in the textbook, if you remember here, speed was the absolute value of the velocity function. Well, in curvilinear motion, the speed is going to be the magnitude of the velocity vector. So instead of absolute value of the velocity, this is the magnitude of the velocity vector, which of course you remember is the square root of the sum of the squares of the components of v of t. And remember, the components of v of t are x prime of t and y prime of t. Okay, so in 11 through 20, it says the position vector r describes the path of an object moving in space. Find the velocity. Now, they're doing space. You and I are just going to do on a flat surface, but it will be on a curve, not on a line. Find the velocity, speed, and acceleration of the object. Now, when they say that, they mean the velocity vector, the speed, and the acceleration. Remember, the speed is the magnitude of the vector, so the speed will actually be a scalar, whereas the velocity, you'll get a vector for the velocity at any time t, and same thing with acceleration. Okay, so here's number 20. You have r of t, the position function, is the components are ln t comma 1 over t. So the velocity vector being the derivative of the position vector, derivative of ln t is 1 over t, derivative of t to the negative 1 is negative 1 t to the negative 2, which is negative 1 over t squared. Make sure you understand this is a vector. However, the speed is the magnitude of that velocity vector, so it'll be square root of the sum of the squares of the components of the velocity vector. Find a common denominator. For the denominator, the square root of t to the fourth is t squared. And this is actually a real valued function, because if I plug t into here, I'll get a number. Whereas if I plug t into here, I'll get a t equals 3 or whatever I plug in. I think they wanted you, didn't say at a particular time, but they could have said at the time when t equals 2. So here you'd get a scalar, whereas here you'd get a vector. And then the last question was, what's the acceleration vector? That would be the derivative of the velocity vector. So the velocity vector was this vector right here. This is, again, you've already done this. The derivative of 1 over t is negative 1 over t squared, so that'll happen for the x component. And then this is negative t to the negative 2, which is positive 2t to the negative 3. Okay, so not very difficult to do. In 1 through 10, it says the position vector r describes the path of an object moving in the xy plane. So we're 2D. Sketch a graph of the path and sketch the velocity and acceleration vectors at the given point. Now, what they don't tell you here is when you go to place those velocity and acceleration vectors, you're going to, the position vector you will draw will be in standard position with the initial point at the origin. But the velocity and acceleration vectors, both of them, you're going to put their initial points on the terminal point of the position vector that you've drawn. Okay, so here we go. To sketch the actual graph, of course, it's really parametric equations. So your choice is to either try and eliminate t if that's possible, or at worst case scenario, make a table. And then, as I said, when you go to sketch the velocity and acceleration vectors, in each case, the terminal point is going to be on the the initial point is going to be on the terminal point of r of t for that value of t. Okay, so here's number 2 is r of t equals 6 minus ti plus tj at the point 3, 3. Now you have to understand that this is an xy point. So since your x is equal to 6 minus t, if your x is 3, 3 equals 6 minus t, that means t equals 3 at that particular moment. If you do plug it into here, then that means t is equal to 3 as well, which should make sense. It should be the same value of t. So I'm going to take this, which right now is in linear combination form, this vector, and I'm going to pull it out as a set of parametric equations. Of course, t is equal to y, so I can take my x and replace the t by y, isolate my y, and I've simply got a line with a slope of -1 and a y-intercept of 6. So that's easy enough to draw as far as the actual original position graph, okay? And of course they want, you should always have direction, so I plug in the t's. Now I'm going to continue this on the next page. Okay, so we already did this part right here. And now we're looking over here at the velocity vector. So what we have, we knew that this was the given position vector. The velocity vector will be the derivative of each of the components. Okay, and then the acceleration vector is the derivative of these, and both of these will be 0. Which is kind of a unique situation because there is no acceleration. Over here, of course, I'm just checking to make sure there's no restrictions on that line that I drew, and of course there are no restrictions. Now, this is kind of a unique one. So what you have is your line. Now, what you're going to do is draw R of 3, because that's what they want you to do. They want you to draw R of 3, V of 3, and A of 3. Now, R of 3, you're actually going to draw it in standard position with its initial point at the origin. Now, this terminal point that's at the end of this R of 3 is going to be the initial point of both the velocity and acceleration vectors. So the velocity vector, it means from the point 3, 3, you're going to go left 1 and up 1, which will bring you to the terminal point 2, 4. So this is your velocity vector. Now, this is a special graph because it's a line. You'll see what I mean when I get to the next one. And of course, this is a special situation because you're going to go 0 left and right and 0 up and down. So you'll just have a dot here for A of 3, just a point.